So kinetics and energetics, this is basically two chapters that I usually combine into one. And it's a very simple topic. There are concepts are simple to understand. And it's basically all about what makes things react together and how we can control how fast or slow that reaction happens or whether we can control it at all. Okay. So this is all about these reactions. So on the left side, you can see a reaction that is a fast reaction. What's happening is that hydrogen is being burnt in presence of oxygen to produce large amount of energy. Actually, I shouldn't say produce, to release large amounts of energy. And that energy allows the rocket ship or the spaceship, in fact, to go into the outer space. On the right side, we have another reaction happening, which is really, really slow. And what's happening is that over here, iron is reacting with oxygen. Over there, it was hydrogen. Now, iron is reacting with oxygen because the conditions are not favorable. We can see that the reaction happens at a really, really low speed. Okay. So, what causes all of this? This is caused by what you call collision of particles. Okay. And these collisions, these relate or these control how fast or slow anything happens. So obviously the fact there is an important factor of time here that we will be considering. And all right, so how do particles react? Particles react when they collide with each other in the correct orientation and in the correct with the correct energy. For example, here you can see that two molecules are coming together and they're colliding head on. Uh, the reaction has happened on the left side, right? But on the right side, you can see that particles are coming together and they are trying to react, but they are unable to do it. So the blue particles remain a blue molecule and the red particles remain a red molecule. Over here, we can see that the red and blue have reacted in creating a new product. And that has happened because collision has happened at the correct orientation or the correct angle. Not just that, it also depends on how much energy these particles have. For example, here we have hydrogen molecule coming close to chlorine molecule. And when they collide together, even if they collide in the correct orientation, it's not possible for the reaction to happen. What's missing is basically activation energy. And once they have that activation energy, now if they collide, they're going to create new substance, which is HCl over there. Okay, so that means these reactant particles must collide with enough energy to overcome whatever energy barrier there is. That energy barrier is in fact called activation energy. For any reaction, there is an activation energy which acts as a barrier. And we will talk about it in a bit. So successful collisions, the ones at bottom, differ from unsuccessful collisions, the ones at the top, by the factor of activation energy. Successful collisions activation energy that allows them to react. Okay, so this is a condition that must be met for any reaction to occur. Now, here is how energy from the discussion earlier on, there are three main things. Number one, the particles must collide. And second, orientation. Must have enough energy reaction to happen, and they must collide with the correct angle. Now, this is how the energy distribution itself when a reaction happens. So this is a typical exothermic reaction. What's happening is that the reactants start at some level of energy. What that value is, we can calculate it, and in IGCSE, you're supposed to calculate it. And we'll talk about it, how to calculate bond energies and know where the particle is. But let's say there is a reactant at a certain level of energy. Now, what happens is that you must provide activation energy to it so that all the bonds in there are broken and it creates a transition state over here. This transition state is when every atom is independent of the other one and they're all acting as a gas. Okay, so transition state has to occur for a reaction to happen. So you take the reactants, whatever they are, you break all the bonds, and you create a transition state where each particle is independent of the other one. Now, once they're at this transition state, they will start to react. And obviously, if activation energy is low, they can get to this state faster. And if the activation energy is high, they will take some time to reach this level. Now, particles get to this state. Every particle is individual. It is independent of the other one. They start to collide. And they're colliding with different speeds. That speed obviously depends on kinetic energy that they have. And what happens is that if they have enough energy, if that particular particle has enough energy, it will collide and it will go down and become a product. When it does that, it releases some energy if this is exothermic process. Okay. And usually in exothermic process, the energy state that it finally gets to is lower than where it started on. But if it was an endothermic reaction, it would end at a state that is higher than the previous one. But in either case, it must absorb energy so that bonds are broken and must release energy when new bonds are made. How much energy is absorbed compared to how much energy is released, that is what determines if it is a uh, exothermic reaction or an endothermic reaction. If more is absorbed and less is released, that is endothermic. If more is released and less is absorbed, then it is exothermic reaction. How does that relate to bond energies? If you want to break a bond, you need to supply energy that is sufficient for the bond to be broken. So to break a bond, you must supply energy. And to make a bond, you get energy which is released. Okay. So that's an important factor that you must remember. And many questions, 3 marks or 2 mark question, they do talk about it. That energy, how does that relate to bonds, or why is an exothermic reaction releasing more energy? So you always start by relating bonds with energy. You say that if you want to break bonds, you must re, uh, supply energy, and if you want to make bonds, you must release energy. And when that happens, if more energy is released and less is absorbed, it is exothermic. And if more is absorbed and less is released, it is endothermic. So where do catalysts come in? Catalysts, as we all know, they lower the activation energy. So for example, in this case, a catalyst will reduce the activation energy, which is the basic barrier, the amount of energy that they need to do a reaction. For example, over here, the green line is telling me that it needs a high amount of energy to do the reaction. But the red line, the one that has a catalyst with it, that is showing that reactant must only gain lower amount of energy before it can do the reaction. So wahi reaction ho raha hai, except with the red line, it's happening with less activation energy. तो जल्दी हो जाएगा ना, because requirement कम है. But and we call this one catalyzed reaction pathway. Why am I calling it a different pathway? Because it is. This reaction is happening through a shortcut that a catalyst allows it to go through. Okay. So remember that whenever you add a catalyst, it lowers the activation energy. And when it does that, it changes the pathway. So it gives an alternative pathway for the reaction to occur. There is a reduced activation energy there. So 3 main things when it comes to catalyst. Catalyst speeds up the reaction without changing itself at the end. Number 2, catalyst lowers the activation energy. And third, by providing an alternative pathway. These 3 factors are important when it comes to the function of catalysts. Biological catalysts are called enzymes. Enzymes allow us to do many reactions that would otherwise not be possible for human body to do, or other living things too. But because of these catalysts, we are able to do it. Another important fact you need to remember is that because transition metals have variable oxidation states, they allow us to do these kind of reactions. Now, be very cautious about one thing. Be aware that you cannot say that catalyst lowers the activation energy. I know that in the past, CIEs have given some MCQs in which that was acceptable, but technically it is wrong, and they have released statements saying that it was only acceptable in those papers. Catalyst gives a different path which has a lower reactivation energy. Okay, so there's a small technicality here that you must be aware of. All right. So how does all of this relate to rate of reaction? So before I go to rate of reaction, I want to talk about what rate of reaction actually is. Rate of reaction is how much the output of a reaction changes compared to time. For example, over here, we have the same reaction, but we have two different graphs for it. This one over here, this is telling me that there's a reactant and its concentration, which means how many particles there are. These are reducing. And this is a curve that tells me that as more time passes, the concentration of reactants is decreasing. Over here, I have a similar graph, except this one talks about product. And I can see that as more time passes, the concentration of the product is increasing. So this is a way for me to know how the reaction is happening and how is it progressing. All right. So how does this relate to our ability to measure rate of a reaction? Remember that rate is gradient. What is gradient? We also call it slope. Gradient is change in y-axis compared to change in x-axis. And we always measure it using a triangle. So for example, if I want to measure the rate over here, all I have to do is make a tangent line over here as I've drawn and create a triangle, this triangle, the blue shaded region. So I can just pick up the values. Okay, what is the height of this triangle? That is 0.4. What is the width of this triangle? That is around 0.2. So I can say that over here, my rate is 0.4 divided by 0.2. So that's really, really fast. It is 2, whatever the units are. For example, it is concentration on the y-axis and time on the x-axis. So I'll say it is 2 mole per dm cube per second. So that is a lot. Every second, 2 moles per dm cube are changing. But compare this to some time over here, for example. You have a triangle here, and this is a tangent, and we can measure the rate at this particular time. So I can take the measurement of rate over here by drawing a tangent again and looking at this triangle, and I can see now that my height of the triangle is a little more than 0.2. So I'll say 0.25 just to be safe. And my width here is 1, 2, 3, and almost 4 boxes. So this is 0.25 divided by, let's say, 0.75. So that is 1 by 3 mole per dm cube per second. So you can see that here the rate was 2, here the rate is 1/3. That is a reduction. And I can see that the rate has reduced over time. Okay, so I can use these graphs to find tangents, and those tangents, I can measure their slope or their gradient to find out how a rate of reaction can be measured. So what do I need? I need to measure the concentration, and I need to measure time when I'm actually performing this reaction in the lab. All right. Okay, so that means rate of any reaction is simply the change that you have. For example, in this case, you have change in concentration. So it will be change in concentration divided by the time taken. So this is just an example. All right. So here's a question. If a reaction happens in which 0.4 moles of gas have been released, and the time taken was 20 seconds, what was the rate of this reaction? And I'll say average rate. What's the average rate of this reaction? So 0.4 moles of gas was released in 20 seconds. So we have 0.4 moles and the time taken is 20 seconds. So we'll simply divide them. Now that is hardcore numbers, and those numbers can tell us how the rate of reaction has changed. If I want to just see how the rate of reaction changes without actually having to measure it, like without actually having to calculate it, I can still see that by using the gradient. For example, over here, if you have this graph, you can see that the product concentration is changing and it is being plotted over time. You can see that over here, if I make a triangle, the graph is steepest. And that shows that the rate of reaction is really, really fast. Compare this to this one or this one, and you can see that the slope of this line, this tangent, is decreasing. And that slope is a measure of how fast or slow this reaction is happening. And by the way, if you come to think of the number of particles here, this slope is an indication of how fast these particles are colliding with each other, how frequent they are compared to time. That is a very important thing to remember, that it is the frequency or the number of collisions that they're doing with each other per unit time. The time is a very important factor that you must not ignore when you're defining or when you're talking about rate. So here in the beginning, I'll say rate is fast, not because there are more collisions happening. I'll say there are more collisions per unit time. And here the reaction is slow because there is less collisions happening, fewer collisions per unit time. Okay, so that is very important, the idea of something per unit time. And obviously over time this becomes almost horizontal, which means that the collisions have almost reduced to zero. Okay, so how do I do this in the lab? Any questions so far? There are three different ways by which these kind of reactions can be done in the lab. And sometimes they can ask you, and this is very important for those people who are going for O levels from this year onwards. And for IGCSE, it has always been important. The idea of designing an experiment. Okay. Now, for example, here's a reaction. Calcium carbonate, which is a solid, is reacting with HCl. Now we know HCl is an acid. Carbonate breaks down when it reacts with acid and produces carbon dioxide gas. So when you're designing an experiment, always think of what observations you can see or what products are made and what how you can collect them. For example, here gas is being released. So I can collect and measure the amount of gas being released. That means I can take a gas syringe. Similarly, you can see that this is an acid and this is a solid. So over time, this solid is going to dissolve. And this is clearly a white solid. So you will actually be able to observe it being dissolved. So that observation, the visual part of the reaction is very important when you're thinking of designing an experiment. So if you're reacting a solid with some solution, the solution is there, the solid is there, the solid is going to gradually dissolve and gas is being released. So you can collect that gas. Okay. So this shows that you can collect the gas, and when you can collect the gas, you can also measure the volume. You can see that these are perforated lines. We say that this container is this gas syringe is graduated, which means it has lines on it that measure the amount. So you can use a graduated gas syringe, and the volume of gas that is produced, you can measure it, record it with time intervals. So the idea of time intervals is also important. You can't say that record it or measure it at different times. That's also fine. But saying different time intervals is better. Why? Because then there's the idea of consistency, there's the idea of uniformity, that maybe you are measuring or recording the temperature after every 10 seconds, or sorry, the volume after every 10 seconds, instead of saying record at different times. So maybe the other person will be like, अच्छा 5 सेकंड पे कर लेता हूँ, अब मैं 25 सेकंड पे कर लेता हूँ, मैं 30 पे कर लेता हूँ. There's no consistency there. But having set time interval, that shows that you are serious when it comes to doing the reaction. Okay. Now, when you take these measurements, you might get graphs like this. So over here, we have volume of carbon dioxide. I told you that anything that changes can be used to measure the rate. So here I have volume of carbon dioxide being produced, and this is time. Now, out of these two, reaction one and reaction two, the green and the red line, can you tell me which one was faster? Yeah, let's see. Let's go back to this slide to see how do we know if a reaction is faster. This one over here is faster, this one over here is slower. And the difference is this is steeper, this is not as steep. So going back to that one, you can see that the green one is steeper. So it has a higher gradient compared to the other one. Okay. So this is faster, this is slower. Now you might ask a question that they're both ending at the same time. Also, they're both producing the same amount of gas. So how can you say one is faster and one is slower? For that, you have to see what volume did they produce in how much time. For example, over here, I can see that at 20, this one reached the value of 20 at just 7. Let me draw the lines to show. For example, if I want to see what value they reached, so at 20, this one reached the value over here. And at the same time, this one reached a value around 14 seconds. So the rate is clearly different, that even to produce 20 cm cube, the green one only took 7 or some seconds, and the red one took 13 or 14 seconds. So obviously the red one is slower, but we can also see that from the gradient of the curve. Now, why is it that they're both producing the same amount of gas? That is because the volume only depends on the output produced, only depends on the reactant amounts that you put in. It does not depend on whether it's fast or slow. You give it enough time, every reaction will produce the same amount if you have the same starting amounts. Uh, it may take more or less time, but the final volume produced will be the same, except if you add more particles. So if you change the concentration, only then will the amount be different. Otherwise, the amount will be the same. All right. So moving on. If you have any questions, then please do ask. So I mean, the green one is faster. All right. Moving on. Sorry. Yeah. Similarly, this is the same reaction, but done through a different set of uh, experimental detail. So for example, over here, the apparatus says that there's a mass balance, and we haven't put the calcium carbonate in, and then we measured it. So calcium carbonate is there, HCl is there, cotton wool is there, so that gas can go out, and it's there. Now you can clearly see an observation. As the reaction happens, there are bubbles. So you can see these bubbles happening. Obviously, solid will also dissolve. So two observations that we can identify. All right, and you can see that the value of mass has reduced. So for example, over here, the value was 120.6, here the value is 120.1. There is a loss of mass. Now, the only case in which there is a loss of mass is when there's a gas being produced. But loss of mass is still a change. So if there is a change, you can use it to to plot the rate, the progress of the reaction, and obviously to measure it. So here's what we are doing. Two different graphs, one is purple, one is green, and you are choosing or you're trying to find out which one was faster and which one was slower. Now this shows that the green line is reaching the same time faster compared to the purple one. The purple one is not that steep. The green one is more steep. The idea is still the same, that it has to be steep, even though in the previous slide there was an increase in the value, and in the new slide there is a decrease in the value. But overall, for example, over here it was increasing and over here it is decreasing. But the gradient determines how fast or slow any reaction is. And over here we are using a different set of apparatus to do the same reaction. So you can check this one, and also you can check this one. Same reaction happening, except this time we are using the amount of gas produced, and in this time we are measuring the change in mass. Okay, so you just need to pick one factor and you can use it to measure rate of change. This is another reaction that you sometimes give in the exam. It is in compulsory one in A levels, but in O levels they sometimes give it. It's simply that there's a mark in there that can be seen. So there's an observer who is able to see this. By the way, what are they wearing over here? What is this thing called? Yeah, we call it goggles. Yeah. So safety goggles or just goggles would be fine. So You can measure rate of change over here by taking the stopwatch and looking at how fast or slow the mark becomes invisible. Obviously, it varies from person to person. Some people are less stubborn, so they accept the change that is as it happens. Some people uh, don't rely on visual feedback as much, and they might think that it hasn't fully gone away or something. So this is a very crude way of measuring rate of reaction, but still it is valid and people do it. For example, this one and this one, if you change the temperature, it will show that this goes away faster than if the temperature was not uh, if the temperature wasn't as high. So, for example, you can also use time on the y-axis and temperature on the x-axis to measure the rate of change. Again, what's happening is that over here we are using the time measured as the dependent variable, and the temperature as the independent variable. So as you increase the temperature, you can see that the time taken is reduced. This is a very unique experiment that is quite rare when it comes to exams. But you must know that regardless of what it is, we have to talk about rate is always the change compared to time, and the gradient tells us which is faster and which one is slower. How does temperature relate to this then? What factors affect rate of a reaction? First one is temperature. At low temperatures, particles have less kinetic energy. So because of that energy being less, the frequency of collision is also less. So they don't move as much, they don't collide as much per unit time. That's very important, per unit time. A very valid point raised by Adina that the previous reaction that we had, this one, can only be used when there is a change in color and a precipitate is being made. Obviously, if there's no precipitate being made and there are other changes, we will not be able to use this experiment. Thank you, Adina. Okay, so this one, for example, we can see that temperature is an important factor when it comes to rate of reaction. You can see that there are two samples of gases here. One is at a lower temperature, one is at a higher temperature. And the one that is on the left, the one at lower temperature, it has lower frequency of collision. When I say frequency, basically I'm saying number of particles colliding with each other, number of collisions per unit time. Okay, so not only are there less collisions, the collisions are also less energetic. So related to what we said earlier, if you want the collisions to have enough energy, only then the reaction will occur. So if they're colliding, but the collision don't have enough energy, there isn't going to be a successful collision. The change isn't going to happen. So clearly, having more energy allows particles to collide with higher frequency per unit time, as well as with higher energies, which means that they have a higher chance of colliding successfully and reacting. So this is an increase in kinetic energy. And if the question asks that how does temperature affect rate of reaction, you have to mention that temperature is related to average kinetic energy of particles, average kinetic energy of particles, which means that at higher temperature, they have higher average kinetic energy, they move more, there are more collisions per unit time, again, per unit time, and so the reaction is faster. Okay. All right. Next factor is concentration. You can see zinc reacting with dilute and concentrated HCl here. In one of them, it is dilute, which means water molecules are abound, but acid particles are very less. So zinc over there, it will obviously have less frequency or lower frequency of successful collisions. Because there are less particles, the collisions are going to be low. And even if they have higher kinetic energy or enough energy to react, the successful collisions are still going to be less in number because particles are less. Compared to that, if you have a concentrated solution on the right side, as you can see, the green bubbles over there, the green particles are supposed to be for acid. And you can see that not only are those acid particles more, there this which leads to them colliding with the zinc particles more. So the reaction is faster because more collisions per unit time. Again, remember to add the per unit time part. Water is still there and water is still the same. It's just that we have added more acid molecules. And another important consequence of this is that because there are more acid molecules, the amount of product made will also be higher. Okay, so this will change both the axis or both the variables that you have. Not only will time be lower, but the amount produced will also be higher. Compare this to temperature or any other factor, the amount will not be changed. Amount can only be changed by increasing concentration or decreasing concentration. That's the only way to change it. Third factor is pressure. Now notice that there's a pattern here. When we talked about temperature, we talked about them colliding more frequently per unit time successfully, and so being able to react faster. When we talked about concentration, we talked about particles colliding more frequently per unit time because there are more particles to begin with, and so the reaction is faster. So the idea of more collisions per unit time is very, very important when it comes to react questions of this. Okay. Now this is another example, another factor. You can see that there is a change in volume. So the particles are still the same. I'm not changing that. But what we're doing is that these gases, we are reducing the volume. So on the left side, the container is bigger, and on the right side, the container is smaller. So what happens is that in a smaller container, they collide more. So another side note, where is the gas pressure coming from? Gas pressure depends on collision of gas particles with the walls of the container. Because the container is smaller on the right side, it has lower volume, they collide more, they react faster per unit time. Compare this to the one on the left side, the gas particles don't collide as much per unit time, which means the reaction is not as fast. Another important thing to remember that this only affects the gases because you can't change the container size in liquids and expect them to collide more per unit time. That won't happen. Okay, so it only affects gases. Similarly, there's another factor that only affects solid. You can see that I have a cube on the top left side, and as I slice it down, new and new sides are being made. For example, over here, it just has 6 sides. But over here, it has all those 6 sides, but there is new side being made in the center. Over here, new sides have formed at the top as well as on the side. And as we keep slicing, new sides are being created, which means that the surface area is constantly increasing. Now, as you increase the surface area, that means there is more exposure for these particles to collide. So if a particle was to come and collide with it, it will collide, it will have more place to come and collide at, which means the frequency of successful collision per unit time will increase. There will be more collisions per unit time, which means the rate of reaction will be faster. Okay. Again, remember that this is only relevant to surface area. Sorry, only relevant to solid. So small particles have higher surface area overall, and large particles have lower surface area overall, which simply means that the rate of collisions is different. And so smaller particles will have higher surface area, more collisions per unit time, faster reaction. Now, regardless of what factor you're talking about, the key idea is that the frequency of collision between reactants that must increase so that there's a higher possibility or higher rate of successful collision happening, which will obviously result in a chemical reaction. Per unit time is an important factor to mention in there. Okay, so that is how energetics and kinetics relate to chemical reactions for O levels and IGCSE. So here's a checklist. These, all of them, you must be able to explain all of it, except for this part in the center. Just ignore this one. I'll put a line over there. Now, how do you measure a rate of reaction of a reaction that does not produce a gas? I'll give an example. Let's suppose I want to measure the rate of rusting. Now, it doesn't produce a gas, but what it does is that in rusting, iron reacts with oxygen from the air, so its mass increases. So I can use the change in mass. Similarly, if I have a reaction where uh, I am reacting an alkali with an acid, and I want to see how fast or slow the reaction is happening, I can keep on checking the pH of the solution, and I can use the change in pH to find out how the reaction is happening. Okay, so any change in the reaction vessel that we can measure, we can use it to measure rate of reaction. All right.